Okay, hi guys. I just want to go through the some of the problems in section C because I think question section A and B is pretty straightforward. Uh, Nothing really conceptual there, but in question C for the class test, I think it's worthwhile trying to just talk through some of the misconceptions there. So this is basically a discussion of section C in the class test. Okay, so the first statement in section C, which you have to check if it's true or false and prove it either way, is that the set W, defined as the set of all matrices of the form A, 2A, 3B, 4B, where A and B are in real numbers, is a subspace of the vector space of 2 by 2 matrices. Okay? So, oops, how is this working? Makes sense. Oops, let's see if I can get this right. So to check whether, so I hope you understand what the subset is, right? It's a set of all matrices that have this form. So, okay, I'm just going to talk you through this question a little bit. So, for example, is this matrix in W? How do I know whether something's in W? Something is in W if it can be expressed in this form, A, 2A, 3B, 4B, for some numbers A and B in R. So, is this matrix of that form? Can I find an A and a B such that 1 is equal to A, 2 is equal to 2A, 3 is equal to 3B, and 4 is equal to 4B? The answer is yes. It'll be of that form when A is 1 and B is 1. How about this matrix? Is 1, 2, 3, 3 in W? No, because if you would A can be 1 and that would cover the top two elements, but there's no value that you could set B to get when B 3 and 3 in the bottom row. If you try to set B equal to 1 to get the bottom left entry correct, you wouldn't get the bottom right entry correct, right? So it's just important that you understand how to tell whether a certain element is in W or not, right? Here is the set of all 2 by 2 matrices, and W is a certain subset. And you need to be able to know whether something is in W or not. Okay, so you just have to check, is W closed under addition? Okay, so let me remove the question mark. So you just take two elements that are in W, like this one, add them together. Note that in my second element, I'm using two different parameters, C and D. Some of you used A and B for the second matrix as well. That doesn't make sense because then I'm adding the same matrix to itself. I need to be able to consider two arbitrary elements of W, right? So the parameters in the second matrix are different to the parameters in the first matrix, but they still have this form. So now I compute. So the question is this in W? So let's compute it. This is, by definition of matrix addition, the new matrix whose top left entry is A plus C, its top right entry is 2A plus 2C, and then bottom left entry is 3B plus 3D, bottom right entry is 4B plus 4D. That's not yet good enough to be able to tell me whether it's in W or not. Something is in W if it takes this form. So I need to be able to write this matrix in this form to be sure that it's in W. So in order to do that, I can write this as a plus c. And then I can take the factor of 2 out here. I get a plus c. Over here I can take a factor of 3 out. Here I can take a factor of 4 out. And it's only when it's in this form that I can recognize that it is indeed in W, because that's, if I take now to my new a, if you like, I'm doing this very slowly for you, but this would be of the form a prime, 2a prime, 3b prime, and 4b prime, where the new a, the a prime is a plus c, and the new b is b plus d, right? So therefore it's in W. This last step is important. A lot of you got to this step and then just sort of said, okay, that's why it's in W. But actually, that's not, just getting to this stage is not sufficient to argue why it's in W. You have to get it to this stage. It's only here that we can see that it takes the same pattern as the matrices in W. Okay. Then you have to check whether W contains a zero vector. Right? So the zero vector, can it be written in this form? That's the question you have to answer. And the answer is yes, because I can write the zero vector as 1 times 0, 2 times 0, 3 times 0, 4 times 0, right? In other words, my A has been taken to be 0 and my B taken to be 0. And in that case, I can clearly see that it has the same pattern as the matrices in W. Right. Okay, I have to check that W is closed under scalar multiplication. So I take a matrix that I know is in W, like this one. That's an arbitrary matrix in W. I multiply it with K, and I check, is the result in W? It's not obvious, because to be in W, I need to check that it looks like this, right? So let's check. This guy here is, by definition, I have to multiply the K in. And the magic is that I can multiply the K in and put it on the other side so that it looks like this. Ka, and then 2 times Ka, and over here I'll have 3 times Kb, and over here I'll have 4 times Kb. And now when I've written the brackets in this way, it's clear that it's in W, because these things that I've taken to be in brackets, I can take it to be my new A and B, right? If you want to make that explicit, you can write this as, this is the same as A prime, 2A prime, 3B prime, 4B prime, where A prime is equal to Ka and B prime is equal to Kb. So therefore it's in W. Okay. So that's how you should really be answering that question. Now I just want to go over, yeah, well that's fine. Let's go to the next question. Okay, the next question is the list f comma g, where f of x is absolute value of x and g of x is x squared, is linearly independent in the vector space of all functions on the real line. Okay, let's check this out. Here's our vector space of all functions. Here's one of the functions, f. Here's another function, g. And is the set containing f and g a linearly independent set? Right? To answer this, So I'm not yet sure whether it's true or false. So let's just first do some investigations here. I need to consider the equation AF plus BG is equal to 0. And I need to ask myself, is the only solution of this where A and B is 0, or are there more solutions? Clearly, if A and B is 0, then that will be a solution. I need to ask, are there more solutions to just A being 0 and B being 0? Maybe when A is 1 and B equals -1, I'd also get 0 there, right? If this is an equation between functions, right? In this equation, the left-hand side is a function, the right-hand side is functions, the zero functions, the function whose value at x is 0 for all x. So if an equation between functions is true, some function equals another function, if and only if the value of the function at each x is the same. In other words, a times f of x plus b times g of x, which is what you'd get if you evaluated the left-hand side at x, must be equal to the value of the right-hand side at x, which is just 0, for all x. Okay? So this equation translates into this equation. It's an infinite amount of equations. One equation for each value of x. Okay, so we've got infinitely many equations. One solution of that infinitely many equations is when a and b are 0. These are equations between a and b. Okay? It's got nothing to do with f's and g's. The equation, the variables we're trying to solve for is a and b. And we've got infinitely many equations for them. Right? Just to be clear about this, I've done it in class, I'll do it again. For example, if we take x is equal to 1, then what is our equation? It means a times f of 1. F of 1 is 1. And I'll write the 1 on the left-hand side, if you'll allow me to do that. That's where we traditionally write the coefficients. Plus b times g of 1. G of 1 is 1 as well. That's our equation when x equals 1. What about when x equals 2? What does the equation say? Well, it says a times f of 2, absolute value of 2 is 2, so I get 2a, plus b times g of 2, g of 2 is 4, so I get 4b is equal to 0. You see, that's the equation when x equals 1. That's the equation when x equals 2. How about when x equals 3? It will say a times f of 3, which is 3a, plus b times g of 3, which is 9. That's a different equation. How about when x equals -1? Then I'll get a times f of -1. F of -1 is 1, so I get 1 times a. And g of -1 is also 1. So this equation here happens to be the same as this equation here. Okay, so some of the equations are going to be the same, but in general you get a whole lot of different equations, infinitely many equations. Okay, now we've got infinitely many equations and only 2 variables, so you should immediately think there can only be a single solution when a and b are 0. Otherwise, there's just too many equations. But let's prove that rigorously. So I can just choose any one of these equations. Which one do you want to choose? I mean, I can choose any selection of these. So I could, for example, let's just look at this equation here, and I don't know, this equation here. You can choose any, you could choose any subset that you want, but I just want to zero in on those 2. Let's call this one equation 1 and equation 2. To satisfy 1 and 2, okay, actually you need to satisfy all these equations, but if you satisfy all these equations, then you definitely satisfy 1 and 2, right? And the only solutions of these 2 equations, as you'll agree with me if you try and solve them, is that a is 0 and b is 0. Okay, so we conclude that the functions are linearly independent because I considered the equation af plus bg equals 0. I showed that this implied that definitely a had to be 0 and b had to be 0, because that's the only way that we could solve these two equations, let alone all the infinitely many equations. Okay, I'm doing this a very verbose way. The short way is in the memo for the test. You don't have to do a long spiel like I'm doing here. You can just say it very quickly. So the answer here is true, right? Now what I want to explain is where some of you went wrong here. So some of you gave some interesting answers. So for example, let me just look them up here. I recorded them at some point. Okay. Let's see. So one class of answer, which is a little bit unfortunate, because I think these are some people who sort of understood roughly what was going on, but they went wrong in some way, was the following. So some people reasoned as follows. They said that the answer is false because look what happens when you take x equal to 0, for example. Okay, so we've got this equation. Most of you guys got to this. You knew that it had to do with how many solutions of this equation there were. But then some people reasoned that when you put x equal to 0, then what have we got? We've got a times f of 0 plus b times g of 0 is 0. And when I sub in 0 and 0 here, I just get 0 times a plus 0 times b is equal to 0. And there's just so many zeros going on there. Well, no, that's not the point is that there are many solutions of this equation, right? For example, I could take a equal to 1 and b equal to 1. That would also satisfy this equation. So therefore, f and g are linearly dependent because there's a and b don't necessarily have to be 0. Now, I hope you guys see the fallacy in this. By the way, a variant of this would be, so let me just give the conclusion there. Right? A variant of this would have been, oh, what about when you take the same equation and you evaluate it at x equal to 1, for example. Then I get f of 1 is 1, so I get a, plus b times g of 1, which is also 1. So I get this equation. And this equation also has infinitely many solutions. So then we conclude that f and g are linearly dependent. Okay, but this is not true, and I hope you guys see the fallacy. The point is that you've only picked one equation, but this equation here, to solve this equation, in order for a and b to solve this equation, they would have to solve infinitely many, this is an equation between functions. In order for a and b to solve this equation between functions, a and b would have to solve infinitely many equations between numbers, as I wrote on the previous page, right? So a and b have to solve this equation, this equation, this equation, this equation, one equation for each value of x. It's not sufficient for them just to solve the equation at some particular value of x. They have to solve all of these equations in order to solve this equation, right? So that's why it's not sufficient to just evaluate this equation at some value of x and then say that the only demand that we're placing on a and b is that particular equation. No, we're actually placing many, many demands on a and b. One equation for each value of x. Okay, let's move on, if we can. Next question, question 3. Okay, this question says the map T from poly 2 to poly 4 defined by T of P value at x is defined to be P of x squared is a linear map. Okay, let's have a look at this. So the answer is true. And the reason is we need to check whether T of P, or whether T is a linear map. You need to check whether T of P plus Q, firstly you need to check whether T of P plus Q is that equal to T of P plus T of Q. And then you need to check whether T of Kp is equal to K times T of P, right? I hope you guys agree that's the two things we need to check whether it's a linear map. And I know in advance and that is true. But if you weren't sure it was true, you could just go ahead and check these and later on make up your decision. Right? So let's take a look at one. What is the left? So I need to prove that the left-hand side equals the right-hand side. To prove that the left-hand side equals the right-hand side, I just need to evaluate the left-hand side at x and show that that's the same as the right-hand side evaluated at x. Right? Because the left-hand side here is a function. This here is a certain element of poly 4. And an element of poly 4 is a function. And the right-hand side is another element of poly 4, a different function. To show that a function equals a function, you need to show that the value of the function at an arbitrary x is the same as the value of this function at some arbitrary x. So that's what I'm doing here. I'm evaluating the left-hand side at x, and I hope to eventually get equal to the right-hand side at x. And then I'll know that the left-hand side is equal to the right-hand side. Right? Once again, to show that two functions are equal, I'm going to evaluate those functions at x and arbitrary x, and if I can show that the values of those functions at an arbitrary x is the same, then the left-hand side function is equal to the right-hand side function. That's what we're trying to prove, right? So let's evaluate this function at x. The left-hand side evaluated at x is this function here. That's the left-hand side function evaluated at x. Okay, how do I evaluate this at x? Well, I need to now go look at the definition of what this function is. This function evaluated at x, the definition of it is you must take this function, p plus q, and then evaluate it at x squared. That's the definition of what t does to p plus q. P plus q as a function evaluated at some number, by the definition of how addition of functions works, this is p evaluated at that number plus q evaluated at that number. But if I look at what I've got here, this is the same as t applied to p evaluated at x squared plus t applied to q evaluated at x squared. Okay, and this is the same as t applied to p plus t applied to q, everything applied to x squared. Okay, hope you guys can see that. Anyway, so that's why left-hand side is the right-hand side. And it's the same for the scalar multiplication one, so you can go and check that. Quite a few of you did get that right, but a lot of you do get confused with you know, the difference between numbers and functions and so on. So, you know, one thing you can't do, at least in this context, is you can't say something like t of p of x. That doesn't make sense. Because p of x is a number, and t is a map from poly 2 to poly 4, so it doesn't accept numbers. You can't give t a number. It has to take a polynomial as input. It has to take a function as input. Okay, I know that sometimes in some other examples I do sort of say t applied to x squared plus 1, but that's a sort of a shorthand. for this. And in an example like this, we have to be careful about the distinction. Okay. Secondly, a lot of you, so let's just look at the question again. The question says, or the statement is that the map T from poly 2 to poly 4 defined by this formula is a linear map. That's the statement. So some of you looked at the statement and reasoned that what's being asked to prove here is that T is a map from poly 2 to poly 4. So what you did then is you went ahead and you argued that, well, if you look at what it does to for example, to the polynomial x, it'll become the polynomial x squared. And you look at what it does to the polynomial x squared, it becomes the polynomial x to the power 4. So it's true that it sends polynomials of degree less than or equal to 2 to polynomials of degree less than or equal to 4. And then you argued that's why the statement is true. But that's not what the statement is saying. The statement is taking it as a given that T is a well-defined map from poly 2 to poly 4. That's not in question yet. It was the very first clause of the statement was saying the map T from poly 2 to poly 4. In other words, I gave that to you. I'm not arguing that T is a map from poly 2 to poly 4 or not. That's not in question. That's on the table and it's accepted. T is definitely a well-defined map from poly 2 to poly 4. The question is it a linear map? That's what you have to check, right? It is definitely a map. Is it a linear map? That's what the sentence is asserting. It's not. It's taking for granted that it is a map. Okay, so just be careful that you can correctly parse the sentence to understand what exactly you're trying to prove. So T is accepted as a map. The statement is that T is a linear map. Okay, let's have a look at the next question. Question 4 says, if B, which consists of the vectors B1 up to Bm, and C, which is the list consisting of the vectors C1 up to Cn, are both bases of a vector space V then M is equal to N. Okay, so there is a theorem in the notes that has to do with this. It's the invariance of dimension theorem, which this is exactly the statement of the invariance of dimension theorem. So you might say true by the invariance of dimension theorem, but that's kind of a little bit too short. You would have got some marks for that, but it's just a little bit too short. You should know instinctively that just one tiny little phrase like that is probably not going to cut it. So if you think back to the notes, you need to be able to think back to the proof of that theorem, and the proof of that theorem was pretty short, so it's short enough to be included as one of these 4-mark questions. So you should be able to reproduce the proof of that theorem here. So if you recall, the proof relies on the bumping off proposition. So B and C are both bases. Hence, they are both linearly independent and span B. Okay, so now the proof set goes as follows. Since B is linearly independent and C spans V, we have that the number of vectors in the list B must be less than or equal to the number of vectors in the list C. That's the bumping off proposition. And similarly, since C is linearly independent and B spans B, we must have that the number of vectors in the list C must be less than or equal to the number of vectors in the list B. That's again the bumping off proposition. So therefore, M is equal to N. Okay, so yeah, most of you answered that sort of fairly okay, but some of you had some misconceptions here along the lines of, for example, that you weren't even sure what the statement was saying. It was sort of as if the statement was saying that my red shirt is red, and you just couldn't understand how that could even be conceivably false. I mean, to prove that a statement is true or false, you have to imagine that the statement could conceivably be false, right? If I say that my red shirt is red, then it's just so obviously true that you just can't imagine why anyone could think that it could be false. But you need to understand that there is well a possibility here that the statement could be false, right? For example, if I were to just adjust the statement a little bit, perhaps if I were to say, if B is the number of people in the English linear algebra class, and C is the number of people in the Afrikaans linear algebra class, then the numbers are the same. And clearly that's a false statement. So how come that sentence could be false and this sentence is necessarily true? It's not obvious that this sentence is true. Just because you've got one basis that has m vectors and another one that's got n vectors, it might have different numbers in them, right? So you might, it might, the concept of a basis might well have panned out that it would have made sense that someone had 3 vectors and that was his basis, and another guy had 12 vectors and that was his basis. That could have happened, and in certain mathematical structures that does actually happen. But it requires some effort to show that for vector spaces that can't happen, that every time someone has a basis for a vector space and someone else has a different basis for the same vector space, then they must have the same number of vectors. I mean, and that requires a theorem. And here is the theorem, or at least the proof, and it uses the bumping off proposition. So it's not something that's just obvious. Okay, last question. Some of you didn't see that there was a question over the page. Very sorry for you. Can happen, I know, but it's one of those things. So here's a question which I think a lot of people had some conceptual problems with, right? So it says there exists a linear map T from trig 2 to R, which sends not R to R2 to 1, 1, cos x to 1, minus 1, sin x to 2, 1, cos 2x to 1, 4, and cos squared x to 2, 5. Okay, so let me just first quickly go through the answer here. What you're supposed to realize, and then I'll explain some of the misconceptions that some of you had. So what you're supposed to realize here, if you stare at these vectors, you should realize there's something interesting going on here, because actually this vector is a linear combination of that vector and that vector, right? Cos, how does it work? Cos squared x is a half plus a half cos 2x, right? Okay, so therefore, if I apply t to both sides, I'm supposed to get the same value. In this right-hand side, we can simplify if we assume that t is linear, we can write this as a half times t of 1 plus a half times t of cos 2x. And t of 1 is 1, 1. And t of cos 2x is 1, 4. So the right-hand side is half plus a half is 1, and half plus 2 is 2.5. On the other hand, the left-hand side is 2, 5. So these guys are not the same. So that's a contradiction, right? If there did exist a linear map which sent these vectors to these vectors, then these numbers, these two vectors should be the same, and they're not. So therefore, t does not exist. Okay, so now let's go through some conceptual errors here. Let's see. I wrote some of these down. Okay, so one person or a number of people reason like this. You say something like cos squared x plus sine squared x equals 1, which is true. And therefore, if you take the value which t sends to cos squared x, and you somehow, so this, so let's just, sorry, shouldn't be laughing here, but it's just it's actually something that's can easily happen. So it's quite important actually. So then the next line is that therefore 2, 5 plus, well, sine squared is somehow 2, 1 all squared. That should be equal to 1. And this statement is clearly a nonsense, so therefore it's false. Actually, that's my take on it. The person who did this reasoned that the left-hand side, there was a more subtle mistake. The thing which 1 maps to is 1, 1. So this is what's supposed to happen here. Now the left-hand side is apparently, how do you calculate this left-hand side? It's apparently, let's see, you just square each entry here. So you get 2 plus 2 squared is 4, so I get 6 in the first entry, and then 5 plus 1 squared is 1, is 6. So yeah, and these are not the same, so that's why it's false. Okay, what's the problem with this answer? The problem with this answer, let me sort of write this answer out more neatly. What this answer is saying is that a linear map preserves algebraic relations and not just linear relations. In other words, what it's saying is that if you apply t to something like some vector squared, then that should be the same as t applied to the vector all squared. That's the kind of thing it's saying, right? Because we're wanting to apply it to, for example, sine x. Sine x all squared is apparently the same as t applied to sine x all squared. So there is such a kind of map which does preserve algebraic relations as well as linear relations, but those maps, but they, first of all, they don't just live at the level of vector spaces, they live at the level of algebras, not just vector spaces, something you guys haven't studied yet. And secondly, a linear map is just a linear map. There wasn't a rule like this, right? So there's a number of problems with this. The first problem is that there's no such notion as squaring and stuff in a vector space. And the second notion is that even if there was such a notion, when we say that T is a linear map, we don't actually ask that it satisfies a property like this. We just ask that it satisfies T of V plus W equals T of V plus T of W, and T of KV equals K T of V. We don't say anything about what happens when you multiply vectors together. Okay, so it's wrong on many levels, but I understand why someone could imagine that it would be true. In some different world, when we're living in the world of algebras and homomorphisms between algebras, then this would be correct. So it's not there's a grain of truth to what that student wrote. Okay, let's see. Another student. Let's have a look here. Okay, let me just write it out. So this student reasoned as follows. I'm just writing out literally what the student wrote. That T of sine 2x, or T of sine x, plus T of minus 3 is equal to 2 times T of sine x plus minus 3 times T of 1. Which is equal to 2 times 2 comma 1 plus minus 3 times 1 comma 1, which is equal to 4 comma 2 plus minus 3 comma minus 3. If you go and look up what T does, again, let's see, do I have it here? There it is here. Right. So T applied to sine x is 2 comma 1, and T applied to 1 is 1 comma 1. So everything's going well so far. Every line is correct. I can't argue at all. Okay, and then the next line is, maybe this is actually, there wasn't a problem with this answer. Let's just see. 1 comma minus 1, that's totally fine. Okay, and then the next line says, but T of cos x is equal to 1 comma minus 1. Okay, and cos x is not equal to 2 sine x minus 3. So therefore, T is not a linear map. Okay. So this is a kind of argument. This is a fallacious argument, false argument, should I rather say, but it's at least it's a wrong argument. You know, sometimes you can have answers which are not even wrong, meaning that you can't even work out what the person is trying to say. So those are worse answers than this. This is an answer which is clear, but it's wrong. Okay, but at least the person has a very clear idea of what he's trying to say. Unfortunately, it's mistaken. So he has a very subtle error that's being made here. And the error is as follows. The error is, suppose I've got a linear map from V to W, T, or even if it is any map, it doesn't have to be a linear map. And suppose that I take some vector A here, and I've got another vector B, which are not equal to each other. And suppose that when I map them over on this side, I get T of A being equal to T of B. That might happen, right? So A is not equal to B, but T of A is equal to T of B, and then this is a contradiction. But this is not a contradiction, because it's totally okay to have two elements that are not the same here, and when you map them over, they become the same. Now, for example, you could map all the vectors to the zero vector, and then every vector gets mapped to the zero vector. So, and that's totally okay. right? So what would be a contradiction is if you had T of A, if you had it the other way around, right? So this is not a contradiction. What is a problem would be if you had it the other way around. If you had it that T of A not being equal to T of B, but A being equal to B. That's a serious problem, because if A is equal to B, then when you apply T to both sides, T of A should equal T of B. This is a contradiction, but not the other way around. It's totally okay for A not to equal B, but T of A being equal to T of B. Okay. Any other problems? Okay. There are a couple more, but I think I'll call it a day. You guys can come and ask me questions after the lecture if you have any further worries.